My study area is located in Indonesia, especially in East Java, and especially in Lampung Bay. Lampung Bay is located 4 kilometers southeast of the Regency and 13.3 kilometers northwest of Surabaya city. Lampung River is the main river in this Lampung Bay system, and then beside this Lampung River, there are 4 surrounding rivers that also give contribution to the sediment transport in Lampung Bay system. Here is the study objective of my research. The objective is to develop full integrated hydrodynamics and morphologic CMS flow models to get the mid-term simulation of topology pattern by analyze the influence of the surrounding rivers to give the development suggestions of the study area. And here is the focusing of the Lampung Bay. Lampung Bay is a tidal flat area. During the spring wave cycles, the shoreline is shifted approximately 400 meters offshore at the ebb tide, and it has characterized as almost zero slope area. And from the Lampung Bay soil classifications, it is classified as the alluvial hydromorph. That means the coastal sediments and river in a size of silt and clay. And the development in eastern region in Indonesia is centered in Surabaya. Because of that, it resulted to the escalations of Lampung region value due to its position among the sea traffic, the domestic interest, and the military facilities. Based on the Surabaya city regulations in 2007, the Lampung Bay is considered as the Zone 1. The Zone 1 has functioned as the port development or waterfront city and large ship navigation line. And to implement these regulations, the governor law was issued in 2012 by giving a reference of reclamation area. But unfortunately, this referral is only considered for the hydrodynamics phenomenon. And here is the wind data is obtained for the 10 years recorded data. This vector-stick plot analysis is give the average and the maximum wind speed. By using the wind loss analysis, the dominant wind is come from the east directions, and the strong wind cycles is occurred during the rainy seasons, that is from October to March. In Lampung Bay system, there are 2 tidal observation sessions. The first one is Karangjamuang and Karangpeto. Both tidal gauge is measured on July 2001. The characteristic of Karangjamuang station is diurnal with an average spring tidal of 0.6, and Karangpeto is semi-diurnal with tidal range of 2.5. In this thesis, I'm using the coastal modeling system flow. The coastal modeling system is an integrated numerical modeling system for simulating nearshore wave current water level, sediment transport, and morphology change. CMS flow is with volume with 2D depth average nearshore circulation model, and it calculates the currents, water levels, and the physical processes as stated here. The CMS flow has framework as these ones, which calculate the hydrodynamics as the first step, then the sediment transport and salinity transport at advance, and then the morphological change in the finals. The current, water level, and morphological change are saved in each computational cell. And here is the governing equations of the CMS flow. This by depth integrated continuity and momentum is derived by Swenson in 2006. And for the model domain, the CMS used the Cartesian grid as its numerical domain, and it is assignment by 4 cells. They are ocean, flow rate, land, and observation cells. For my study, it is divided by 2. They are preliminary and simulation domain. There are 3 boundary conditions of my domain. The first one is water surface elevation as time size proceeds, the wind and river flow as 1 year return periods. And for the model control, it has 2 sections. The first one is preliminary section to calibrate the numerical results and obtain the model parameter that been used for the simulation section for 1 year. And for the model calibrations, the first one we have to observe the data from Karangpeto. In Karangpeto, in the hours of 360 seconds, it was suspiciously light and mystic. But from the other populations, this 367 data can be ignored, and all of the population data in Karangpeto can be used as the observation tools. In the other hand, in Karangjamuang, the observed data, the observed period is 2 weeks. But from the Geospatial Information Agency, it is recorded that the period is 12 hours. Because of that, it was suspected that there was an external force that affects the recorded data, and we need to analyze this one. The analysis is using by the filtering signals. It is by subtracting the observed data and with the average water levels. And the comparative value is shown here. The green value is the result of the filtered data, and the red dot is from the BIG pattern envelope. From this one, we can know that there is a high difference between the filtered data and the BIG pattern that it can be concluded that current geometry gauge cannot be considered as one of the calibration value. And here is the data source and the time for the preliminary sections. And here is the result of the calibrated data levels in the preliminary sections. It shows that the calibrated and the observed data, the calculated and observed data has a good agreement, even though it has slight differences because of the observation stations and observation cells has a difference of 11.522 kilometers. For the next analysis, we have to include the wind forcings from the both season, rainy season and dry seasons. Here is the results of the each seasons. From this one, the residual current and morphological change shows that the main component that influence current in this study is the tidal current. And here is the residual current pattern defined in the preliminary simulation results. And for the results and discussions, as mentioned before, that there are 5 alternatives in simulation sections. The existing design is the same as the preliminary sections as I discussed before. And here is the designs as referred by the Governor Law in 2012. And this is the alternative one that I made by erasing the C area to maintain the navigational line here. And then as replacement, I add the new C area just at the eastern side of the B area. And for the alternative 2, it is almost same with alternative 1, but those two line separated area are combined by a new B big area. And in alternative 3, the chosen reclamation type is mixed reclamation type. The reclamation is combinations of the line separated line and line connected type. And here is the input data for my return alternative. This is the vector stick plot analysis for the wind forcing data for whole 1 year. And this is the total area of each reclamation alternative and the model parameter that obtained from the preliminary sections. And here is the simulation result of the existing conditions. The existing condition shows that the high rate of erosion is located here, and there is no huge impact on the Lamont-based systems. And for the existing designs, the high rate of erosion is located here, just at the north side of the reclamation area. And unfortunately, the existing design for Governor Law showed the highest rate of erosions. And this is for the alternative one. The alternative one shows that the erosion and accretions happen in the gap between the alternative. And the erosion and accretion pattern is almost in balance in these situations. And for alternative 2, it is almost same with the alternative 1, that the erosion and accretion pattern is occurred in the gap between alternative, and the erosion rate of this alternative is higher than the alternative 1. And this is the alternative 3. It is saying that the erosion and accretion pattern is occurred at the gap between each reclamation area, but this reclamation type has the lowest erosion rate of all. And this is the comparisons of all simulation from the existing condition and existing design. We can see the difference. And then the alternative 1 and alternative 2, it shows that the great erosion pattern is occurred here. And this is the alternative 1. From the 5 simulations, I can make a comparison in this table. And then it shows that the existing design has the highest erosion rate, and the alternative 3 has the lowest erosion rate. From that results, I can make the conclusions that the lowest erosion rate is occurred in the alternative 3, and low erosion means tends to stable from the morphological change, and the stable changes means it is advantageous to the development of this area. And then with stable changes, the lifetime can be longer. When the lifetime longer, the operation and maintenance implementation and cost will be easier to implement, and the cost is cheaper. So thus in Pulau Galang area from the governor is decided as the bird conservation area. From this alternative 3, the post-midterm simulation shows that there is no high erosion rate or sedimentation rate in this area. And then it can help maintain the Pulau Galang as it form and shape, and for these existing conditions for the longer lifetime. So I suggest that alternative 3 is the best solutions for the reclamation area in Lamong Bay system. This is all of my presentations. Arigatou gozaimasu.